Okay. Hello to everybody who's watching this recorded. So, the first question is somebody asked in the chat, quiz 5, question 3. So let me go ahead and pull that up. Is there any like large conceptual questions or anything you guys have before we dive too far into it?
I have a question. I don't know if
Yeah.
if I read it right, but for linear
Okay.
dependent, like is it
hmm
only linear dependent if the scalar plus the column equals 0?
The scalar plus the column.
Like the
Um,
last when you row reduce? I
if
don't know
the
if I
scalar
read that
plus
wrong.
the um, I don't think that's something that is considered. When you row reduce, it's dependent if it's not a pivot. If that column is not a
Okay.
pivot when you row reduce. Okay.
Okay. Okay, cool.
Cool. Question 3. So I'll go ahead and do this question, and then I'll talk about some more conceptual stuff. So 5, question 3. Nope. You guys can see my screen okay, I assume? Yeah? All right, cool. All right. Question states, we're going from R2 to R2, being a transformation that rotates the vectors by 90 degrees counterclockwise that reflects across the line y equals x, then reflects across the line y equals x. So there's a couple ways to do this. I'm going to do it first geometrically, just by like seeing how it moves on a graph, and then I'm going to do it considering like the actual algebra and constructing matrices from there. So let's draw our graph. We have the point 1, 0, okay, because that's what it says here. Find t of 1, 0. So this is the transformation of that point 1, 0. Okay, so it says the first thing that we do is we rotate the vector by 90 degrees counterclockwise. Okay, 90 degrees. That moves us to 0, 1. Okay, and then we're reflecting across the line y equals x. So we're flipping right back to it, and we should return right back to 1, 0. Let's double check to make sure. So this one, in this particular case, you can think of it as nothing really happens to this point. So that's how you can think about these sort of questions geometrically. You draw the point and you kind of move it part by part through each transformation. The way to do it with matrices is we'll call it A1 and A2 are our two matrices, okay? So X is what we're putting in, all right? So that's our point 1, 0, or vector 1, 0. A1 is the first transformation, okay? And A2 is the second transformation, all right? So you can think of like, remember this is equal to B, just moving from X out is the order that we do it. So that's how we write those matrices. So the rotation for counterclockwise, this is the formula you guys really need to know. Cosine of theta on the diagonal. Negative sine theta here, sine theta here. Okay, this is for a counterclockwise rotation. For a clockwise rotation, it is exactly the same formula, except it is opposite of counterclockwise, so your theta is negative, okay? So in this case, we're rotating 90 degrees counterclockwise. So the cosine of 90 degrees is 0, and the sine is 1. This is what that matrix looks like, and this is the first thing we do, so this is A1, okay? And our second rotation, we're flipping across the line at y equals x, which is just switching x to be y, and y to be x. So these are two matrices, and then we multiply 0, 1, 1, 0 times 0, negative 1, 1, 0. That'll give us our total transformation matrix. And then we multiply that by the point 1, 0. That'll get us our point. Yeah, and you'll find out that that will be 1, 0, I believe. Okay. Cool. Any questions on that one? Fantastic. And again, you can just ask questions in chat as well, but turning off your mic works equally is fine. So there are a couple other questions on different examples and the midterm and homeworks and stuff, but I'm just going to talk about column and null space first, just to get more of like a conceptual background. So column space of A is just like a reskin of what we did for the first test. Okay, it is exactly something that we did in the first exam and all of you did, but it is just a different term. Column of A is just the span of the columns of A. Okay, and null space, a little bit trickier, but still something that we've been doing this whole time, is the solution set 2ax equals 0. Okay. Fundamentally, that's what column space and null space are. Okay. So something that you have done in the first exam, just with a different set of words to it. Okay. And in terms of dimension, okay, so the dimension of the column space of A, okay. So thinking back to the first exam, we talked about like the column spanned a plane in R3, right? Where the plane was like R to the number of pivots. So the dimension of this is still kind of the same idea. It is still just the number of pivots. Okay. And then dimension of null of A, conversely, is the number of free variables. Okay. Or the number of not pivots. Okay. And for the dimension of the column space, it's the same thing as the number of not free variables. Okay. And then the rank nullity theorem. So this is rank. Okay, just the same thing, but a different term. Again, kind of annoying, but whatever. And nullity is just the dimension of the null space. Okay. So you can think that rank of A plus nullity of A. Okay, so we have a number of pivots plus our number of not pivots. Okay. So that is equal to our number of columns, which is the same thing as our number of variables. Yeah, so that, which is, I believe, for an m by n matrix, is just n, is how they write that. Okay. So the number of columns. Any questions about rank or nullity?
I have a quick question. So
Yeah.
if there's two dimensions, like it's a 3 by 4, then the max number of pivots for that would just be 3, right? Because
The max number of pivots would be 3, yeah,
yeah, okay. So then the rank of that would be 3
at most.
at most. At most is what, yeah.
Yeah.
Okay, that makes sense.
Yeah,
Thank you.
so you'll always have a nullity that is at least 1, right?
Yeah.
Because you always have at least one free variable, is the same thing that says.
Okay. Cool.
Does
Thank
that
you.
make sense? Yeah,
Yeah.
cool. The basis theorem and the inverted matrix theorem. Yeah, so just on the note of column space, what a basis is basically just it's the column space without any redundancy. Okay, so while like we talked about earlier, like the span of 2, 1 and 4, 2 is the same thing of span 2, 1, right? We're just removing that redundancy because 4, 2 is linearly dependent of 2, 1. So a basis would just be the vectors without any redundancy. So we would say the basis of this is 2, 1. Okay. Well, I'm sure we'll get to talking about inverted matrices later on, so we'll come back to that one. But a basis for the column space would be your pivots, and the basis for your null space would just be the parametric vector form of like your matrix. So this is exactly the same stuff how we did for the first question. I don't know if inverted matrices are on this exam. Can somebody answer that for me? Yes, they are. Okay, cool. All right. All right, so any more questions about this stuff right now?
I have a
Subspaces and
question.
linear. Yeah, go ahead.
So why does the parametric vector form form the basis for the null space? Like just why
Yeah.
is that happen?
Okay, so and I'm gonna post this PDF, so if you guys miss something like 30 minutes after the exam, after this review, I'll post it and you guys can see it. So, but when we do parametric vector form, right, we have like x1, x2, x3, x4 equals, we'll call x3 and x4 free in this case, okay? So I'm just making up a vector here, okay? There's no particular reason that I'm doing it this way. Okay. So we have, this is like our solution set to x equals 0, okay? For just some general a or whatever, all right? So the reason that these vectors form a null space is because we know that there's no redundancy in these, because for each free variable, right, there's going to be some row where it is the only one that has an entry, right? Because for a free variable to happen, it has to be x3 equals x3. So regardless if there's x4 plus, like, if we go even bigger with other variables and whatever, there's only going to be one entry in the third thing all the way across, right? And it'll only be for x3. That's why we put it in row reduced echelon form. I know that x5 doesn't make sense, but that's just me like talking generally about this sort of stuff. So these two vectors form your basis for your null space, okay? Again, what you did for the first exam, row reduce, put it into equations, put them into vectors, then you have the basis for your null space, okay? It seems a lot more complicated than it is, but again, the same sort of stuff you did for the first exam. So does that make sense? Did that answer your question? Cool. Any other questions about this? Just thought of solution set forming a basis. Cool. Right, so that was the definition of basis there. Somebody asked. Subspaces and linear independence. Just while I'm going over conceptual stuff, I'll go ahead and talk about subspaces a little bit. So subspaces. So I'm going to go through the three qualifications of it. Yeah, so the basis of column of A, I'll just write this down just so I have that written with the other parts of the notes. Basis of col. Only your pivot columns or linearly independent columns. Okay. Basis of null equals just your vectors from parametric vector form. Okay. All right. Cool. So on the note of subspaces, there are three main qualifications that you have to consider. And I promise I'm going to get back to the other more like algebraic and like written questions in a moment. I know they're backed up in the chat, but I'm going to get there. So subspaces, you have three qualifications. 0 gives the 0 vector. Okay, so you can just think of this as like 0 in has to mean 0 out. Okay. So if I give you like define something as transformation of x, y, nope. Or like something like that, right? Defining like a transformation of x, y that is like x plus 1, y. When we plug x in, when we plug 0, 0 in, we get 1, 0 out. So this this qualification fails. So it would not be a subspace. So if any one of these three qualities fails, then it is not a subspace, okay? So 2, closed under addition. So any two vectors in the space can add to be within the space, or have to add to be in the space, okay? So a good way to think about that is we have graph, and I have my span, okay? If I pick a vector, and I pick a second vector, if I add them, they're going to stay on this line, okay? Okay, so whatever I add on here, they add together. You can think if you have a plane in R3 that goes to the origin, whenever you add two vectors, it'll still be on the plane. Okay, think of it as within the span of that sort of stuff. Null space and column space are by definition subspaces. So if either of those ever occur, you know it's a subspace. Okay, so if it says like for the given matrix A, is the solution set to AX equals 0 a subspace? Always yes. Okay. I'll talk about why in a moment, but the third quality is that it's closed under scalar multiplication. Okay, so how that works is if I have some space, I'm on a plane, and let's say this space is this square surrounding the origin, okay? If I have a vector that goes like this, okay, and I multiply it by 5, it's out of the space, and that fails, okay? Another example would be if it's just like a positive version of a line, like if it just goes here, right? If I take this vector and I multiply it by -1, it is no longer on that original line, so it's now out of the space, and it fails to be closed under scalar multiplication, okay? I'm sure we'll go through a couple examples where we talk about this and we go through it. Go through each of these steps. Another note, so this is how you check. You can do all of those things, or if it can be described as a matrix, it's a subspace. Okay, so if it gives you some big, like, let's say I give you t of x, y, z is equal to 3x plus 2y plus z, y, negative 6z, okay? Can we describe that as a matrix? Sure we can. We're putting in x, y, z, so the matrix would be 3, 2, 1, 0, 1, 0, 0, 0, negative 6 times x, y, z. And how I got that matrix was I just read it like line by line for equals to b, okay? So my first entry is 3x plus 2y plus z. So that's me just reading off that top line by coefficients, okay? So if we can describe any of these transformations as a matrix, we know it's a subspace, okay? That's the reason we do linear algebra, is we're talking about subspaces, but in order to do this, you have to think about what is a subspace and then what can we do these operations upon. Okay. What can you not describe as a matrix? If, like, in some cases, they'll give you, like, transformation of xy equals xy greater than or equal to 0, or something like that, you know? Or, like, the absolute value of x, you can't describe in a matrix, right? That's how you can kind of think about that. Yeah. So, yeah, it's not always as clear as they're just, like, giving you this, like, list of equations, right? If this is the case and there's no, like, +1 or anything, because we can't really describe, like, +1 in matrix multiplication, then you can just assume that it's a subspace and be done. But you have to be very, very careful about that. Try to stick to this stuff over here, but that's just a nice shortcut. It's a really ugly star. Okay, cool. That's subspaces in a nutshell. We just check each of these qualifications. If all three pass, then it is a subspace. All right, now I'm going to start looking at some other examples, and I'm sure we're going to go through one-to-one, and subspace just lives in some greater dimension of thing. So like in this case here, right, there's 3 entries, right, in this output vector, not just x, y, z, okay? So we have 1, 2, 3, so it's in R3, okay? That's what that means. However many entries we have out, that's what dimension it lives in. You can kind of think of it as. That shouldn't be anything too insanely complicated. But think about like column space and null space, right? Column space lives in your number of rows, and null space is the same thing as is the same thing as a solution set. So it lives in your number of columns. Okay. R to the number of columns is the space it lives in. Okay. All right. Any questions about this stuff? Cool. All right. Practice exam question number 4. Cool. That's not the right one. I did that one wrong. Okay. So, comes in 3 parts. I'll leave this question for. Let me just double check. Yep. So, the first question says a matrix A whose null space is the line y equals x. Okay. So null. So if it's equal to the line y equals x, that's the same thing as the vector 1, 1. Okay. And we don't like x1 to be free, so let's call x2 free. Okay. Because it's in R2. Right? And then whose matrix transformation has the range equal to the z-axis. Okay. Range equal to the z-axis. So we start in R2, okay? Because it has a null space in R2, so that means it starts with 2 columns. And it has a range in R3, so that means the number of rows is 3, okay? And if the range is the z-axis, what does that mean for the first 2 rows? Anybody?
It's 0.
Yep, they have to be 0, because we're getting 0x and 0y, right? And then whatever happens for this bottom row is, we don't quite know. That is defined by the null space, okay? So, going from this to these equations here, right? We have x1 equals x2, which is x1 minus x2 equals 0, which means when we row reduce, we have the form 1, -1, 0, right? But we don't know how many rows there are because every row could be exactly identical, right? Because we could just row reduce and get rid of all of them. So let's make this really easy for ourselves. The bottom row is just going to be 1, -1, okay? It can be any form of like 8, -8, or -4, 4, or anything along those lines that matches the form of this, okay? Does that make sense? Again, it's okay if something doesn't make sense. If you have a question, odds are somebody else has the same question. So feel free to ask, and I'm like, it's fine. You can't ask too stupid of a question, I promise.
How'd you start out with that null A, like with the arrow and x2, 1, 1?
Yeah.
How'd you
So
do
it
that?
says that the null space is equal to the line y equals x, right? Which is just, it doesn't have to be 1, 1, but I like for as many as my entries as I can to be 1, because whatever my x is, my y has to be, so I'm just calling it 1, 1, okay? Yeah. So, the reason that we like that is because we want x2 to be equal to x2. We don't want it to be equal to negative x2 because then we have to do some tricky stuff. So I like to try and find where my like y is equal to 1, okay? And that's how I got that vector. Does that make sense? Where I then got that vector 1, 1.
Makes sense. Thank you.
Yeah. So could the rat? So yeah, that's not in the chat. Someone said so. The null space of y equals x is just x minus y equals 0. So 1, -1 could be the last row basically. You're kind of skipping a couple steps there, but in essence, yes. Just try to stick to this form of like drawing your vector or writing out like the parametric vector form, getting the equation, putting it in a matrix. You can do all of that in one step, but you really, really, really should write this down because negatives can get kind of confusing if you just try to skip steps. And yeah, the first two rows are 0 because of the range, because the range is just the z-axis, which means that x and y are both 0, okay? So like when we set this equal to, it's just 0, 0, and then something, some number when we multiply by x. Okay, so that's A. For B, write two non-zero vectors in x. Write two non-zero vectors x and y in R3 such that ax equals ay, but ax equals does not equal y. So this way you can kind of think of it a little bit more intuitively, but I'll talk about how to do it like the right way or like the long way you can think about it. So one way to do it, I would say x equals 1, 0, 0, right? And that's equal to 1, 2, negative 4. Okay? And another way to do this is okay. Another way to do this is if we say y is equal to 0, 0, negative 0.5. And you'll see that that gives you 1, 2, negative 4 as well. Okay. So I do that by just seeing that the first and third row are linearly dependent upon themselves. So I find two x and y that give me the same thing based upon that relationship. Okay. Another way you can do that you could find the null space is what you could do. So you row reduce this to get REF of A equals 1, 0, negative 2, 0, 0, 0, 0, 0, 0. Okay. So, this gives us the vector x1, x2, 3 equals free variable x3 times present twice there, 0 times for x2, and yeah, 1 for x3, plus x2, 0, 1, 0. So another way that you could have done this without making it more complicated is do x equals 1, 0, 0, and then y equals 1, 1, 0. Okay. But regardless, we get to this form. And from here, we have to pick vectors in the span of this. Yeah. So this is just the intuitive way, but if you picked two vectors that are linear combinations of this, they would still give you the same result, which would be b equals 0. Okay. So for instance, we'll find that 2, 0, 1, x equals this implies b equals 0, right? Because we solved for x equals 0. And we'll find if y is equal to 0, 1, 0, we'll also get b equals 0. Okay. Different way, but same thing. Okay. It's more like assigning a b. You can just find the null space and go from there. Okay. Questions on that one? I'll go over the properties of invertible matrices as well at some point. Okay. So I'm going to move this to the side so I can do the last part. All right. So let A equals that. Clearly draw a column of A and null of A. That's not what to do, but okay. So when in doubt in linear algebra, take a matrix and row reduce it. REF of A, 1, negative 2, 0, 0. Okay. So where is our pivot? Our pivot is just the first column. Okay. So column space of A. So the basis of the column space of A is 1, -2. Okay. So draw a graph. 1, -2, 2, -1. Like that. That's the column space of A. Okay. Just drawing the span of your pivot columns. All right. As for null of A, all right, so let's write this in parametric vector form. We have x1, x2 equals 2, 1, x2. So the basis of null of A is 2, 1. So we draw that as 2, 1, 2, -1. Draw this one in blue. That is your null of A. Okay, so that's for C. Alrighty, questions on that? If my arrow only points one way, is it still correct? Technically, no, because you can multiply it by negative numbers. So it has to, you just continue it going the other way. Okay. Because then you're just drawing a vector versus a whole span. All right. Cool. So that's that one. In this case, yeah, you could put both in the same graph. It doesn't really matter. Just make sure that you clearly label them. And we can do that because they're both like in R2 in this case. But if it was like a wider or taller matrix, then we could not do that. All right. I see someone's asking for number 2 on this exam as well. For the one person who asked for number 2, is there any particular part of it or the whole question? Because there's 4 parts, so. We find the columns of A by taking the pivot columns of the row reduced form, okay? So when we were here, we just took our pivot in that corresponding column. Okay. That's to question 2. And my office hours are tomorrow if you guys have more questions. Or you can just email me, post on Piazza, whatever. All right. You do not need to show works in part A to C, but show work in D. Alrighty. So let V equals the span of this. So let's find the dimension of V. So the dimension of the span of vectors. Okay, so they asked for part B specifically, but we'll go through each one because parts A and C at least are pretty quick. And part D we can talk about inverses and do that one as well. So, how do we find the dimension of a span? Anybody? Column space. Yeah, it's the same thing as column space, but what defines the dimension of it? Yeah, the number of pivots. Yeah, pivot columns, number of linearly independent vectors, number of pivots, number of not free variables. All of those things mean the same thing, which sucks. But it's just something you have to get used to. Throughout the slides for this like set of like material specifically, I know for like one-to-one and onto. In that PowerPoint, there's a list of equivalencies just so you can see what all things mean exactly the same thing. Okay. So what's the dimension of this? The dimension of this is 2 because we have 1, 2 pivots, no pivot here, no pivot here. All right, so question B says that it is an 8 by 5 and the range is a line, okay? You can think of range just as the column space, okay? So if the dimension of the column, or if the column space is a line, what is the dimension of the column space? It's equal to 1, okay? So now using rank nullity, we have rank minus nullity equals number of columns, or plus nullity, sorry. So our rank is our dimension of column space, which is 1. We don't know our nullity, so I'll call it some variable x. Number of columns is 5. Okay. So in this case, x is obviously 4. Null is a 4-dimensional subspace of, where does the null space live? It lives in the number of columns, like solution sets do. So it's in R5. Okay. So C talks about onto and one-to-one. Yeah, so someone asked, is the vector, just as like a sidebar, is the vector 1, 1, 0 in the span of 1, 0, 0 and 0, 1, 0? The way you can check that is you take your two vectors and you take the one that you're seeing if it's in the span of, okay? And if it's consistent in span, if it's not consistent, linearly independent, or outside span. Same thing. Okay. Yeah, so talking about B, we're talking about the null space of A, okay? And the null space of A is solution set. And solution sets, okay, so it is the solution set to AX equals 0. That is what null space is, okay? It's just a term to shorten saying find the solution set of the equation AX equals 0, okay? So all solution sets are R to the number of free variables in R to the number of columns. All right. The number of columns is 5 in this case. And we have to find a number of free variables, but we only know the range. So the range, the dimension of the range is the dimension of like how many not free variables we have, okay? That like number of pivots, number of not free variables. Okay, so that is 1 because it's a line, right? A line is only one dimensional. There's only one way to move on a line. Okay, 1 degree of freedom. So that's where we get the rank nullity equation, and that's where we can plug that in. Or you can think of it as not pivots plus pivots equals total number of variables, right? Or total number of columns. So that's where we get that number 4, because 4 plus 1 has to be equal to 5, the whole space that it is in. So a line created by one free variable. So in this case, the line isn't created by one free variable. It's created by one linearly independent vector. So it's talking about the span of the columns. It's not talking about variables in that case. So this is the range of the transformation is a line in R8. Okay, because that's where the range is. Okay, that's how you can think about that. So the rank is 1 in that case. All right, let's move on to talking about one-to-one onto. So one-to-one and onto are very important things that tell us a lot in a lot of different fields. So particularly in cases like robotics or like thinking about like frames of reference and like things like that. One-to-one and onto are extremely important ideas because it's how we get to somewhere and how we can get back, or if we can get back rather. So one-to-one. Do this little diagram every time I talk about it. So one-to-one and onto. Okay. Similar but not the same. Okay. And there's an easy way to find both of them. So one-to-one is, so this upside down A means for all B within the codomain. Okay. Again, this is just math notation. It's not meant to confuse you. I just don't want to write a bunch of words. So this is for all B within the codomain, or just for all B. There is at most one solution. Okay? So the system either has a solution or is inconsistent. Okay? So if it has at most one solution, that means it cannot have any free variables. Okay? And if it has no free variables, what does that mean for the number of pivots? So there has to no free variables means there's a pivot in every column. So the number of pivots is the same thing as the number of columns. Okay. So these go both ways, all of these things. Okay. So the way you can find it is a pivot in every column. That's right call. Okay. So the way to think about that is here's our code, here's our domain. Here is our codomain. Okay. So this is where all of our x's live. These are all of our b's. And what I'm saying is wherever the range is, okay? So the column space, this is the same thing as the range. For every x over here, there is one b that it corresponds to, okay? All right, so this whole space gets mapped to here, okay? This is kind of how you can think about it, like mapping it down. But this comes with a caveat. The caveat is we might not be able to reach everywhere, okay? And the reason that we like this is because given some b, right, there's only one way to get there, so we can find our way back. Okay, we can find the x that corresponds to the b if it's 1 to 1. That's why it's one of the qualifications for invertible matrices, which we're going to talk about more in a second as well. So again, in the slides, I encourage you to go back and look at the lecture notes. There's like a list of equivalencies that all mean the same thing for 1 to 1. Okay. Yeah. So the big thing here is no free variables and number of pivots is number of columns. But the way that they'll ask you this in like a true or false question or a short answer question will be like this. Okay. All right. So on to very similar in wording with the exception of a single word. For all b in the codomain, there is at least one solution. Oh. So when I say solution, I mean x. There's one way to get there, okay? So in this case, there's at least one solution. So does that mean there can be free variables? Yeah, there can be free variables. Doesn't really tell us much about it, but like there can be infinitely many ways or there can be one way to get there. All right, but there's no b that it's inconsistent, okay? So what does that mean for the range and the codomain? What's the like comparison of size there? If we can get to all b's, what is our range equal to? Is it smaller than our codomain, bigger than our codomain, or equal to our codomain is what I'm asking. Yeah, the range, it has to be equal, right? Because it can't technically be bigger because it lives in that space. So you can't have like an R3 and R2. Yeah, so that's how you can kind of say that, okay? So the range equals the codomain, okay? So that means number of pivots equals number of rows, right? Because we have that many linearly independent vectors to get us the whole space. So you can also think about that as column space of A is R to the number of rows, okay? So drawing this on a diagram like we did before, blob, blob. So if we can get everywhere, okay, at least one way, we can get to each B. So this whole space is the codomain. So this is codomain, or this whole space is the range. One thing to note, though, is there might be multiple x's that map to the same B, okay? That's tricky. So in this case, we can't go back, but we know this whole space is filled, okay? So the codomain is just like the space we're moving. So it's like the dimension of B or the number of rows, okay? R to the number of rows. Okay. So any questions about these two as is, right? So this just means pivot in every row. That's how you check, okay? This is like the main way to check this one. This is the main way to check this one, okay? But again, remember number of linearly independent vectors equals dimension of codomain. Again, I'm writing all these things out of redundancy because they are the same thing, okay? Saying any one of these things mean the same, except for this, but this is just, like this one here doesn't mean all the other things. But that's just me saying it to like talk about the free variables in terms of that. But all of these other things are on those slides that I was talking about. And again, I encourage you to look and compare things. So, any questions about one-to-one and on-two? I'm going to go over 2C. That's what this is leading to. Okay. All right. So the reason that we want both of these things is because if there's one way to get there, and we can get to all B. Okay. Then, based on X, we can find B, obviously. Find a unique B, and based on any B, we can find a unique X. Okay. So this just goes to say, think about talking about the codomain here, right? There's one way to get back, but if our range is the whole codomain, we can get back and forth between the two spaces at will. So we call this qualification down here invertibility. Okay. That's what an invertible matrix is in essence, is it is both one-to-one and on-two, so we can go back and forth between two spaces easily. All right. And again, we'll talk about how to find that, exactly what that means in terms of determinant, stuff like that in a moment as well. We still have another like 40 minutes, so. All right. So, talking about all of this for onto and one-to-one. All right, I'll move those notes over there. Click here. Suppose that T's are n to Rm, okay? So Rn to Rm. N is where we start, M is where we end, okay? So we can draw the matrix like that. It's a linear transformation with standard matrix A. Cool. A is a matrix. Fantastic. Which of the following is guarantee that T is one-to-one? So this question is asking which of these mean the same thing of one-to-one, okay? So one-to-one, pivot and column. Pivot in all columns. The way you can think about this in terms of like verbiage, one-to-one, there's one way to get there. Onto is we span onto the whole codomain, all right? One-to-one, there's that one. One way to get there or no way to get there, all right? Onto the whole space of the codomain. So if it's one-to-one, okay, that means there's one way to get everywhere or no way to get everywhere. So there's at most one way. So for this question, it asks, for each x, there is a unique y such that tx equals y. this is one is a little tricky because there is the single qualification that like it says for each x there is a unique y so that tx equals y so we're trying to get to all y's is what this is saying, I believe. But we don't get to all y's. There is a unique y such that. Yeah. Yeah, so this is just the definition of a transformation here. Okay. Yeah, sorry, I almost confused myself there. So there's for each x it gets us a y, but it doesn't tell us. Okay, so it's kind of confusing in terms of verbiage. It says each x gets us one y, okay, but a different x can also get that same y, okay. All that it's saying is you put in an x and you get out a single y, okay. That's what this statement means. It is just worded in an extremely confusing manner. So that one is no. Okay. 2 is for each y. The matrix equation ax equals y is consistent. So that would mean that we can get to all of our y's. Or that is onto, and onto and one-to-one do not mean the same unless it's square, because number of pivots is number of if you have the pivot in every column and you have an n by n matrix, then you have a pivot in every row as well. So part 3 says the columns of A are linearly independent. If they are linearly independent, you have a pivot in every column, and that is true. Okay. Questions on that one? Yeah, this verbiage sucks for I. That's stupid, but whatever.
I have a question.
Yeah, go ahead.
So, could you like go a little bit further into like why I is incorrect?
Yes. Okay.
Yeah.
So does that mean there's a pivot in every row for the last one? It would for I if it was square, but all right. So for each x, it gives us a single y, okay? There is a unique y. So I understand why this is what they're thinking when they write this, but I understand how confusing it is. So what they're saying is each x gives a single y, okay? But how one would typically read it would be each x gets a single y, and no other x can get there, okay? But they don't explicitly say that each x's y is independent of each other, or is unique. So the way that they use unique in this is just a very like particular case, and I don't like it. I would get confused on this just because I would probably ask someone the question of whether or not it is just stupid. Like I'm sorry. So what they're saying is every x gives us a single y, okay, but it doesn't specify that each different x can give us like okay. So all that it's saying is each x gives a single value for a y, okay? And while it says unique, it means unique in the sense that when you put in x one time, it won't give you a different one the second time you put it in, okay? Does that make sense? And I recognize, like, as I'm like walking through it, like how confusing this question is. But does that kind of make sense?
Yeah.
Okay. It's okay if you say no to that. That's totally okay. Yeah, so that doesn't tell us if there are more x's or if like more x's go to a single y or not. So it doesn't make it on one-to-one. Okay. 2 is false because getting to all y is not the same thing as being one-to-one. That is the same thing as being onto. Okay. If it were square, then that would be true. But for each y, the matrix equation is consistent. That's only talking about that there's like at least one way to get there, because there can be infinitely many ways to get there as well. All right, now for part D. All right, invertible matrices. So the only thing you're going to need to be able to do quick and fast is a 2 by 2 invertible matrix. In no other class ever do they ever expect you to be able to do a bigger invertible matrix fast, okay? So you can assume if they give you like a 3 by 3 or something like that, it'll be pretty easy to invert. But nevertheless, invertible matrix for a 2 by 2 A, B, C, D. Inverse is 1 over the determinant times D, A switched, negative B, negative C. Okay, and the determinant of A equals AD minus BC. Okay, so main diagonal minus other diagonal. They're called the major and minor diagonals traditionally in a 2 by 2, but main diagonal, the one you think of, and then the reverse diagonal is minus. Okay, so that's for 2 by 2. As soon as you know that formula, you can just plug it in and be done. So this question says if A is 2 by 2 and A inverse is that, a thing to note is A inverse is just A. Okay, so you can just take the inverse of this matrix and it'll give you A, which I'll do in a moment, but I'm going to talk more about invertible matrices before that. So how do we do it if it's a 3 by 3 or larger? Okay, so there's not an easy formula, which sucks, but the method to do it is row reduction. For an n by 2n augmented matrix, where let's give you the matrix 4, 0, 0, 2, 0, 3, 8, 5, 2, augmented with the identity matrix. Okay, and you row reduce this. Get identity. Then right hand side is A inverse. Okay. A way to, if they give you some giant matrix and they say find the inverse of this, and it's like 10 by 10 or something, okay? Step 1, to see if you can find the inverse of a matrix, it has to have a pivot in every row and column, and it has to be square, okay? Has to be 1, 2, 1, and on 2. Okay, so that's going back to that same idea that for every x we can get to a b, and for every b we can get back to an x. Okay, and it has to be square. All right. So the implications of 1 to 1 and on 2 in this case are any of those, if any of those conditions fail. Okay, if there is a free variable, because that was one of the conditions of 1 to 1, if all of the columns are not linearly independent, then it fails being 1 to 1. If there's a row that doesn't have a pivot, like if there's a 0 row, or if there's 2 rows that are similar, or 2 columns that are similar, all of those things mean it's not invertible and you can throw it out immediately. Okay, so if they gave you the matrix like 4, 2, 8, 0, 4, 2, 9, 0, and 18, 24, pi 0, and then 1, 1, 1, 0, okay, that bottom row is all zeros, so you know it can't have a pivot there, so you already know it's not invertible. And then you don't even bother with the row reduction or any kind of stuff like that, okay? That's just like a sanity check to make sure that that's something you can do, okay? For a 2 by 2, it's pretty easy. Just see if you can row reduce and not get a 0 row. But for this question, it gives us a specific matrix. So this matrix is A inverse equals 5, 4, 2, 2. So this is A inverse. And how do we get from A inverse times something to be the identity? Okay, what goes here? A inverse times A is always the identity. That's the purpose of an invertible matrix, okay? Or that's the purpose of an inverse. So this is the same thing as A inverse inverse. Okay, you can think of it kind of like that. If you tried to work backwards in this process, you would find yourself getting probably very confused very fast. But what we're gonna do is we're just gonna run through that formula, okay? So switch A and D, make B and C negative. Okay. And then outside, 1 over the determinant, which is 10, which is 5 times 2, minus 4 times 2, which is 8. Okay. So this is equal to 1/2. 2, -4, -2, 5. Which is 1, -2, -1, 2.5. And if you really wanted to check yourself, to find this is A, you can find the inverse again, and you'll find that it's 1 over the determinant, which is 2.5 minus 2, 1 over 0.5. Switch those, 2.5, make that negative, 2, 1, 1. Okay, and 1 over 1/2 is just multiplying by 2. That's 5, 4, 2, 2. I'm rushing through that part because that's just algebra. Not really much to understand there. So that's just like a way to check your work. You by no means have to do that and are expected to do that. But if you have extra time, I suggest doing this sort of stuff, okay? Does that make sense? Are there questions on invertible matrices in terms of this? Okay. Okay. That was question 2, which took quite a while, but that's okay. Now we've talked about invertible matrices, null space, column space, onto and one-to-one, and that's pretty much everything you guys have been talking about, because this is exactly, I believe, 4 weeks since your last exam, so that's a month of content at least. Yeah, so let's just start bumping down some questions now. Yeah, I'll scroll up a little bit. Just zoom out. Okay, so some of them have gotten lost in the chat a little bit, so if you could resend questions, that would be fantastic. True or false questions in number 1. Yeah, let's run through some true or false real quick, and then I'll do 7B is what somebody had asked for. Problem 5 as well, and problem 6. Okay, so pretty much the whole practice midterm. All right. Okay, if vectors v1 to vp, so let's call this some matrix, there's p columns, okay, form a linearly independent set of vectors in Rn, okay, linearly independent set of vectors, okay, that means there's a pivot in every row, right, in Rn, linearly independent set, then it has to at least fill up the whole space, okay? So because if P is greater than N, that means that there's linear dependence. That would be true, okay? So the way to think about that, hey, I have all of these vectors that happen to be linearly independent. So can they exist in a space, like, if I have 4 linearly independent vectors, can N be 3? No, right? That doesn't make sense. We can't have 4 different directions in a 3 space. So there is a 4x7 matrix that satisfies dimension of null space equals 1. So how many pivots can we have at most? I'm going to post this recording in an announcement. We're going to have 4 pivots at most, right? Based on our number of rows is more limiting, okay? So we're always going to have at least 3 free variables, okay? So dimension of our null space has to be at least 3. All right, so this one is false. And if you have questions on this, please stop me, turn on your mic, just ask questions. Yeah, C is for an n by n matrix, okay? In the matrix transformation, given T of A is on 2, so that means pivot in every row. That's n pivots, which is the same thing as our number of columns. So we have a pivot in every column as well because it's square. All right? So suppose A is n by n, and it has only the trivial solution. Okay? So if it has only the trivial solution, that means all vectors are linearly independent. Okay? Then each B in Rn can be written as a linear combination of the columns of A. All right, so then each B in Rn, so what this is asking is are all B in column space of A. So that is the same thing as asking if something is onto, right? If we can get everywhere, it's the same thing as being onto. That makes this one true. I think the answer keys talks about the invertible matrix theorem. Yeah, you can read that, and it's just talking about like onto and one-to-one stuff. Same sort of idea of like everything we've been talking about with invertible matrices and onto and one-to-one stuff. Okay, so suppose vectors 1, 2, 3, 4 are vectors in R5, such that span v1, v2 has a dimension of 2. So that means those two things are linearly independent. And span of 3, 4, vectors 3 and vector 4 have a dimension of 2. Then the span of all 4 must have a dimension of 4. That's false because we can just say vector 1 equals vector 3 and vector 2 equals vector 2 or vector 4, right? Because then we just say the same thing twice, and that tells us absolutely nothing, and then the span of all 4 of them is just 2. Oh, why the hell did I just circle that? That's definitely false, and I definitely said false. Yeah, so someone asked me to go over B again. So B says there's a 4 by 7 matrix, which I've drawn over here. Okay. So can there exist a 4 by 7 that has one single free variable or a dimension of a null space of 1? At most, we can have 4 pivots, right? Because that's how many rows we have. That's the smaller number. That's how many pivots we can have at most. Okay. If that is the greatest number of pivots, then we have our least number of free variables, but we still have more than one. We have 3. Okay. So since we have 3 free variables, we can never have less than that. All right. So dimension of null space has to always be greater than or equal to 3. So it cannot be 1, so that part is false. All right. Any more questions on number 1 before I move on?
Hey, I have a question for D.
Sure.
I thought column of A lives in Rm, but then it asks then for each B in Rn.
Yeah. So this is because it says A is an n by n matrix, so it's square.
Oh.
That's because they're not using the m notation. You're on the right track though. You're right for sure, but that's the little caveat that it comes with being square.
And then for A, if P is less than n, then P is the number of columns, right?
P is less than n.
Uh-huh.
Yeah, P is the number of columns because that's how many vectors we have. Sorry, can you say that again?
It would be a tall matrix.
Yeah.
And then if
That's
it's
one way to think about that, yeah.
Okay, never mind. I answered my own question.
Okay. So yeah, this is going just to say, like, can this qualification be true in something where it's tall or square but not wide? Okay, that's the same thing that this is asking. Rows and columns sort of stuff. I just kind of talked about it in terms of like space and geometry and things. Once again, one of the things with linear algebra is there's like 10 different ways to explain every problem, and unfortunately not every way clicks for everybody. So you just have to put in a little bit more work than you may need to, or you may think that you need to. So I see people asking to do questions 6, 5, 6, and 7, basically the whole thing. So we'll start with, let me look through these real quick. Yeah. Let's just start problem 5 and work our way down real quick. Problem 5 is just talking about a matrix in particular. Another important thing to think about with this exam and all exams in general for your time at Tech, time yourself when you do like a practice exam, just so you make sure that you're aware of the time constraint, because that can be kind of tricky sometimes. Just a bit of advice there. So T is a transformation from R3 to R2, being T of X is equal to Y minus Z, and let U transformation counterclockwise by 90 degrees. Okay. Find the standard matrix A for T. All right. All right. So for the matrix T, just going like row by row for our Y minus Z, how many X's are present? 0. How many Y's are present? 1. How many Z's are present? -1. For this bottom one, we have X plus 2Z. Okay. We have 1X. Oh, that's 2Y. That's not 2Z. Y. That's a 2 there, and that's 0Z present there. Okay. That is our matrix A for T. For U, it's the counterclockwise rotation matrix. Okay. Cosine theta, negative sine theta, sine theta. Counterclockwise 90, so a theta of positive 90 degrees, 0, 0, -1, 1. Okay, now let's go through these. So A and B, done and done. Is T on 2? Okay, so is this matrix A on 2? Does it have a pivot in every row? Yeah, right? Yes. Is U invertible? Yes. All rotations are invertible. Always, always, always. You can think about it geometrically, is if we rotate everything by 90 degrees, and we pick a point, we know exactly where it started because we can unrotate it, right? So invertible just means in a geometric sense, you can undo something, okay? All right, circle the composition that makes sense. So which one can exist, you can think of it as. So T of U would be A times B. Okay, that's our matrix B. Okay, A is a 2 by 3, B is a 2 by 2. And to check if we can multiply matrices, we draw a box around the middle number. Is this number the same? No, therefore it cannot be multiplied. For BA, it's a 2 by 2 times a 2 by 3. Okay, draw my box once more. That is the same thing, so it can be multiplied. So that's our answer. And it would result in the two numbers outside of the box, a 2 by 3 matrix. And then F says write the standard matrix for the composition you chose in part E. So that's B times A, 0, -1, 1, 0. I know I'm moving a little fast, but please ask me or interrupt me as if you have a question on something where something didn't make sense. Times 0, 1, -1, 1, 2, 0. Okay. And now we matrix multiply. So I like to do it 1 or 0, -1, 1, 0. And I put my second matrix on top. Okay. 0, 1, -1, 1, 2, 0. And I draw my little bridges. Okay. So we always line up the values on each bridge is how I can think of it. And then down here, this bottom part is B times A. Okay, that's what that part is. So this top left entry, 0 times 0 plus -1 times 1. And then the next one, -2 and 0. And then going on to the bottom row, we have 1 times 0 plus 0 times 1 is 0. 1 times 1 is 1. 1 times -1 is -1. This is our resulting matrix. Okay. That is EA. -1, -2, 0, 0, 1, -1. Okay, that's question 5. Any questions on that one?
Yeah, I have a question on
Go ahead.
So for part B,
Yep.
how does that work?
Part B. So we're writing a standard matrix for U, okay? But U is Um, U is our counterclockwise rotation, okay? So being from R2 to R2, so it's a 2 by 2 matrix, okay? For rotation matrices, you can always, always, always use this formula here, okay? The only thing is, if it's clockwise, okay? Think if we're here, we're going counterclockwise. And if we're going here, we're going negative counterclockwise, okay? So if it's clockwise, it's negative angle, okay? So you just plug in a negative and go from there.
Thank you.
Yeah, cool. So someone said explain C again. Yeah, T is onto because there's a pivot in every row of A. That's why that is true. That's the condition for finding an onto matrix. So me doing the bridge thing is I take my two matrices A and B, and I write them in this form that I learned in pre-calculus, like I guess a lot of years now. I was in 10th grade in 2016. Yeah, so like 6 years ago. But I write it like this. Oh, well, I'll keep it consistent with a notation for this. But this is matrix B, this is matrix A. I write it B, and then I write A above it, and then I make a matrix down here that is equal to BA. All right? So how I do it is for this entry here, I start with my entry in the row, and I multiply it by the same entry in the column. Following my bridge is how I think about it. I also tutor pre-calculus, so this is how I teach my high schoolers about this stuff. So for that same entry, we take the other thing in the row, we follow that bridge, and we multiply that number by the corresponding entry in that column. Then we add them. Okay, so for this first one, for this entry of -1 here, we follow 0 times 0 plus -1 times 1. That gets us -1. For -2, we take the same row, and then we find the column that it aligns with. 0 times 1, then -1 times 2. So that gives us 0 plus -2, and that's how we do that. And then we go through there. Just like a simplified way to think about it instead of a big formula. All rotation matrices are invertible because they are, by definition, onto and one-to-one. Okay. Just think if like I have a plane and I turn it, I can just turn it back, right? So that's why it's invertible. So that's the bridge thing. How do I find the BA matrix? You just multiply the two matrices together. 6A. Yeah, we're getting to 6. Don't worry. Yeah, okay. I think that's that. All right, question 6. I'm just trying to get as much in as I can before time runs out. And I'll stay a little bit later, but regardless. Question 6. All right. So parts A and B are unrelated. Find the standard matrix for T. So we have a matrix A, B, C, D. Okay. And we transform it by, when we transform the vector 1, 0, we get out 1, 2. Okay. So this is the same thing as saying A times 1, 0 equals 1, 2, right? Okay. Let's write this back in that notation that I like to multiply matrices in, okay? So now we have a 1, 0, and we have our 1, 2, and we have A, B, C, D, which we don't know yet. Okay? So now we form these little equations based on it. So for this entry, we have A times 1 plus B times 0 equals 1, right? And that says A equals 1. And then for this 2 down here, we have 1 times C, remember those bridges to follow, plus 0 times D equals C equals 2, right? So now I can come back over here, and I can just replace them, all right? So that's how I do the first part. And then for the second part, I'm given a different transformation. I'm giving the transformation of a times 1, 1 equals negative 1, 1. Okay? So now my negative 1, 1 goes down here, and I have 1, 1 up here. Again, please interrupt me or tell me I'm going too fast or ask how I'm doing things. But here, now we have 1 times 1 plus b times 1 equals negative 1. All right? And that means that b equals negative 2. Okay? And then for the second entry for this one, we have 2 times 1 plus 1 times d equals 1. All right, so that means that d equals negative 1. So now we write the matrix, negative 2, negative 1. And that is our matrix. A equals 1, 2, negative 2, negative 1. So are we multiplying A by separate 1, 1? Yeah. So our input or our x is 1, 1, and our b is negative 1, 1. Okay, so I'm writing it that this is my A, this is my x, and this is my b, because A times x equals b, right? So I just like, if it's A times x, I just move x up, and then the product goes here. Okay, cool. Any other questions on part A? Okay. William Moreland has put the matrix A in its row reduced echelon form. Write a basis for columns of A. Pretty easy. Remember our basis for columns of A? Pivot columns. Okay. So that's this column and this column, or rather this and this. 2, 3, 4, and 7, 10, 12. Cool. Write a new basis for column of A so that no vector in your new basis is a scalar multiple of any of the... Oh, okay. So what they're asking for here is a way to combine these two vectors to give us a basis that gets us the same thing, okay? So to explain it geometrically in essence, right? If I give you a basis that's 1, 0, and 0, 1, right? They span all of R2 in R2, right? Another set of vectors that does that is 1, negative 1, and 1, 1, okay? These span the same thing, but they're constructed by two different vectors that are not scalars of each other, okay? So the easiest way you can think to do that is just v1 plus v2 and v1 minus v2, okay? So you're just trying to get some linear combination of the things that isn't just as simple as a scalar, okay? And there's still no redundancy because this and this are still linearly independent, okay? Does that make sense? So for part 2, I'd say 9, 13, 16, and 5, 7, 8. Okay, this is just adding, this is subtracting. Would it also work if I do v1 plus v4 and v2 plus v3? Yeah, that should work. Yeah, that'll work as well. Same kind of idea. You're just finding two vectors that construct the same span, right? But still not redundant. There's still no linearly dependent vectors within your basis. So, cool. Good. 3, find one non-zero vector x that satisfies ax equals 0. Well, we're given our row reduced echelon form, so let's move that into parametric vector form. We have x1, x2, x3, x4 equals, what are our free variables? We have x2, negative 3, x2 equals x2, 0, 0, plus x3, 7, 0, 1, 0. Okay, so find one non-zero vector that satisfies ax equals 0. It is any linear combination of these two. Okay, but why make your life hard? Just pick one. Make it 7, 0, 1, 0. And you're done. Okay. Yeah, so that one would probably be a headache to grade, honestly, because there's so many different ways to do it. But regardless, anything in the null space satisfies that condition. So any questions on 6 before I move to 7? And this is someone asked a homework question, and I'll do that one, and we'll go over whatever else we can, or with a little bit of extra. That's not too long. Cool. Okay. Oh, what the hell? That's not what I want. So this is an example particularly of something you can't model as a matrix, and then you can't just jump and say that we're done with subspaces, okay? So, subspace question. And it lists this out very nicely for us to go through the 3 conditions, okay? Parts A and B are unrelated, whatever. All right, so plug in x and y equals 0, okay? Is the condition satisfied? Yes, okay. Someone asked about 6. Is 2 minus 7 negative 5? Yes. I just did v2 minus v1 because I like keeping things positive. It's easier on my brain. Yeah. So, is v closed under addition? So, or what's the easiest way to think about this? So, we have u and v that satisfy these conditions, okay? U equals u1, u2. V equals v1, v2, okay? And u1, u2 is greater than or equal to 0. And come on. v1, v2 is greater than or equal to 0. So, now we have to think about what would be true or not. So, let's think. So, when we add them together, our goal is that u plus v, transformation of u plus the transformation of v equals transformation of u plus v, okay? All right. With the condition still satisfied. So we have u1 plus v1, u2 plus v2. Okay. So u1 plus v1 times u2 plus v2 greater than or equal to 0. This one's a little bit tricky to think about algebraically, but you can kind of think of when would this go wrong? It would go wrong if we added the things together and one of them flipped signs, okay? So it's not saying that by xy is greater than or equal to 0. It's not saying that they are both positive numbers. It is saying that they have the same polarity, which is saying that they have the same sign, okay? So xy is greater than or equal to 0 just means that x and y have the same sign. So they're either both positive or both negative. Okay. So we can work this out algebraically, and we get u1, u2 plus v1, 2 plus v2, u1 plus v1, v2 greater than or equal to 0. Okay. where this gets tricky is obviously this is greater than 0, obviously this is greater than 0, but we have to talk about what goes on here. Okay. Something to like consider, you can kind of think of it as, is going here. These two things have to have the same sign. All right. I wouldn't go this far and do all this algebra. Once you get to this point, this is where you have to like really think about what you're doing and what the question is asking. Okay. So there's a couple cases, U is positive, both negative, and V is both positive, V is both negative. So let's just try, for example, if I have like 4 and 0.1 plus -3 and -1, okay? Obviously, when I add these two together, I get 1 and -0.9, and the transformation of this, right? -0.9 is not greater than or equal to 0. So that is not true, is how you can see that happen there. Or you could walk through this algebraically and do much more of a headache. But I would consider this here, and I believe that the solution gives like a specific example, and you just have to think about like things switching, particularly in this case. So moving to 3, is it closed under scalar multiplication? If we have C times U1, U2, okay, this is equal to CU1, CU2, which then gives us C squared, U1, U2. Is that greater than or equal to 0? This is always positive because it's square. This is always positive because that was given. So that is true. All right. Questions about that one? All right. Moving on to B. Yeah, so this question, what it is asking, this is actually a null space question. So this is written, this transformation here, which is the same thing as saying 1, -5, 6 times our x vector equals 0, right? Interesting. So find a basis for W. So you can do this by finding the null space, or what you could do is you could just find two linearly independent solutions for it because it's a plane, so two vectors are going to come up with it, or two vectors are going to compose it. So let's pick x1 to be 1, and let's pick z to be 0. Okay, so what does my middle entry have to be? It has to be, well, pick y to be 1, all right, because we have two free variables, right, y and z. So let's pick two different cases. So we'll pick this case, and then we'll find that x has to be 5. And we'll find for the second case, we're going to switch it. We're going to set y to be 0 and z to be 1. In this case, x has to be -6. These are two linearly independent vectors that compose that plane or that space. All right. Here, in this case, right, talking about the null space of it, it's already in reduced row echelon form. So we have x. In this case, it's x, y, and z, but it's the same sort of idea. Equals y, 5, 1, 0, plus z, -6, 0, 1. All right. This, just picking two different values for x and y that are like, or for y and z that are just 1 and 0 and 0 and 1, will always get you two linearly independent things. Makes your life really easy. Or you can just find the null space, which in this case is also pretty easy. So that's your basis for I. And then II. Is there a matrix such that the columns of A is equal to W? Okay. This is where it gets a little tricky. You have to think about this a little bit more carefully. So the basis of W is these two vectors. Okay? That's the basis. Now we're asking what column space constructs those two, like, can we have a column space where those two vectors are two vectors? Sure we can. Let's just make A 5, 1, 0 and -6, 0, 1. Okay? In this case, now we have our column space being constructed with those two vectors. And that's everything that it asked for. Okay. How do you know that it wants a basis of column? Well, that's what it asked for. Is there a matrix such that column of A is W? Yeah, I'll go back over. Find a basis for W. Oh, you know that it doesn't want the basis of the column space because it's writing this. That's an eraser. It's writing this equation here, right? This is our x vector is x, y, z, right? So this is a matrix A times x equals 0, which is the definition of our null space. Okay. You can't really write in this notation a column space, not intuitively, at least. So, or
So,
if they do, they'll see. Go ahead.
so do we automatically assume that we are finding the basis for a null space if there's an equation equal to 0?
Yes. One equation equal to 0. Yes. Yeah, because that's what it is, right? But you have to make sure there's no constants, right? 0 in, 0 out has to be true. Okay. Fantastic. So, what are my office hours? My office hours are tomorrow from 3 to 4:30. In Skiles 2:30. It's also on the Canvas homepage. Yeah. So that's how we find the basis of the null space, and very, very carefully for 2, talking about the column space being the space constructed by the null space. Very confusing set of terms, but it's just asking, hey, here are 2 vectors. Can there be a matrix that's column space for those 2 vectors? And sure they can be. Cool. Any other questions about this one? Cool. Are there any other questions before we call it for the night? I know someone asked for a 7AII. Yeah, I'll go over that, and then I'll go over the homework question that someone asked, and then I'll be done for the night. Okay. So going back for question 7II, the reasoning for it is because you can come up with a counterexample pretty easily. I did go over subspaces earlier in the video, just about the 3 qualities of them. And then checking is this process, which isn't always as annoying as this. Okay. But you're basically just finding 0. You're checking to see if 0 is 0. These are the 3 things you have to find. These are what define a subspace. Closed inner addition, T of U plus T of V equals T of U plus V. Or rather, do these things still make sense? Are they still true? Okay. So in the context of this question, we're more talking about this part here. And when we add the 2 vectors together, does it still make sense? So does it contain, is it closed inner addition? So the easiest way to think about it is the only time when x plus y is not going to be greater than or equal to 0 is if we have one that's positive and one that's negative, okay? And essentially what that boils down to is can we come up with a couple numbers such that A1 plus B1 is positive and A2 plus B2 is negative, right? Because what we're looking, if this is true, then it fails, okay? This is the only kind of question they'll ask in this format. There's not a, the only other way they would ask this if it's less than 0, which would be the same kind of idea, okay? This is a very specific question, that is what I'm saying. So, can we come up with an A1, A2, such that when we add a negative B1, B2, it's positive and negative? Sure, we can, right? Or rather, we can think of it as A1 minus B1, A2 minus B2, okay? So all that's saying is A1 is greater than B1, and A2 is less than B2. Okay. Can we find 4 numbers that is true for? Sure, we can. They're not only limited to being positive integers. That's true. Yeah, because it says here that they're in R2. So that just means they're real numbers. It doesn't mean that they're integers or positive or non-zero or zero or anything. Okay, so that's our choice to pick and choose. All right, so cool. Where was that homework question? I saw it somewhere in this chat. Homework 3.6, problem 10. The inverse of a matrix. Problem 10, there's 10 problems on this thing. Damn. Okay. True or false question. And again, if you have any additional questions or whatever, just email me or come to my office hours or post on Piazza, whatever you feel most comfortable with. Okay. So A is 3 by 3. And lambda, real number with the property ax equals lambda x, satisfied by some non-zero vector x. For each question, select true or false statements. So this is actually something called an eigenvalue. I'm not going to explain what that is at this point in time because that is like the whole last third of the class is we're going to be talking about eigenvalues. But essentially all it means is ax equals lambda x or something, okay? So satisfied, blah, blah, blah. A minus lambda is invertible. Yeah, that doesn't make sense, right? Because it's a 3 by 3 matrix minus a single number. And what the hell does that mean? Right? That's false because that doesn't even make sense. Okay? A is not invertible. Okay? A might be invertible. Okay? We don't really know. Yeah, there's not really an easy way to like think about that. This is some complicated stuff, and it's meant to make you think about what's going forward in the class. You shouldn't. I'm not going to say that just on the off chance that there is this on the exam, but I wouldn't say this is a very likely thing to be tested on or put on an exam, because these are the only things that they would talk about here. A minus lambda I is not invertible. Okay. Okay, so this is saying, write this equation out, ax equals lambda x. Writing that backwards, we have ax minus lambda x equals 0. All right, and the way that we can think about this is we're multiplying each entry by a single number, right? Like if we have a matrix that's 3, 3, 3 multiplied by x, right? That's just equal to 3x, okay? So a minus lambda times I, so that's just moving it to a matrix notation, okay? Equals 0, okay? Okay, so a minus lambda ix equals 0, and x is not, it says, I'm trying to read through what they're trying to explain it as so I don't go too far forward and explain the qualities of eigenvalues, but yeah, since we can't, okay, yeah, it says a non-zero vector x, okay? And if there wasn't inverse, it would be a minus lambda I inverse times a minus lambda I, right? Times x equals a minus lambda I times 0, which is just 0. So these two cancel out, and we're left with x equals 0, but we're given that x is non-zero. Okay? Therefore, it is not invertible, so C is true. And we don't have enough information about A to talk about whether or not it's invertible, so we don't know again, so that one's false. You're welcome, Megan. Cool. Any other questions about anything before we go? Sorry we ran a little bit over, but it happens. Cool. All right, well, you guys have a great night, and thank you for coming. Good luck tomorrow, and for those of you who are in Section D, I'll see you then. Thanks, Emma.